So let's start by thinking about the big picture and the location. We're looking at a neuron. So here's the soma or the cell body of our neuron. Here's the axon, and then here's the terminal. And when we think about a neuron, it's going to have a resting membrane potential of negative 70 millivolts. And just to reiterate what this means is that inside of this neuron has more negative charge, whereas outside of this neuron has more positive charge. Okay. So what we're describing here is how we establish this state. This is the constant resting state of a neuron. And how do we establish that? Based on the movement of sodium and movement of potassium. So the first thing we need to establish is the different permeabilities, right? The different permeabilities. The idea that potassium's permeability, and we represent permeability with this large P. So the permeability of potassium is 25 times greater than the permeability of sodium. Okay. Then we want to start by thinking about our cells. So let's look at our cellular makeup here and the various channels and pumps on the cell membrane. So here's our cell. We're going to first put on the sodium-potassium pump because you know this is always existing on the basal surface of our cells, and its function is to pump 3 sodiums out. So let's put 3 sodiums in here, they're going out, and 2 potassiums in. Okay. And remember we said that the sodium-potassium pump is directly responsible for 80% of the resting membrane potential, but about 20% directly responsible for the resting membrane potential, but about 80% indirectly owed because of the gradients that it creates. So this is our sodium, potassium pump. Let's now identify our channels. So if we said that the permeability for potassium is 25 times greater, this means that there are more potassium channels. So let's represent that here with 3 potassium channels. And remember, these are simply passageways, so these are not active. These are still employing passive transport according to the concentration gradient. And in comparison to that, we have fewer sodium channels. Okay, so more permeability for potassium than for sodium. Now let's begin to think about our relative concentrations. So inside the cell, we have more potassium, right? Remember, we think about our sodium-potassium pump, pumping potassium in. So inside the cell, say that again. Let's start with sodium. Inside the cell, we have less sodium. And then outside the cell, we have much more sodium. Okay, so greater concentration for sodium outside our cell. And then for potassium, that is the opposite. We have a greater concentration inside the cell. And then a lower concentration outside the cell. Okay, so when we think about that, let's kind of make a note of that here. The second thing we need to consider is the concentration gradient. In other words, the chemical driving force. And based upon what we just described, we know that sodium moves into the cell because it's at higher concentration outside, lower concentration inside. So sodium moves into the cell. Okay. The opposite is true for potassium. Potassium has a greater concentration inside the cell and a lower concentration outside the cell. So potassium moves out of the cell. So that's the first scenario we want to think about. Now, as those ions move, as more sodium leaves than potassium can enter, because we can see that the number of sodiums leaving is greater, then we begin to think about the polarity of the cell. So now we can make mention of the negative charge. There's going to be abundance of negative charge left behind as more sodium leaves than potassium can enter. So now we have a negative charge inside the cell and a positive charge outside the cell. Okay. So now we can consider our electrical driving force. That would be the third step here. Is now that we have a polarity established, we can think about where both ions will be attracted based upon their charge. And in this instance, sodium would want to get inside the cell because it's positively charged. So sodium moves into the cell. And potassium, likewise, will move into the cell because it is also positively charged. Okay, so that's our chemical force and our electrical force. So let's illustrate that with some arrows here. So if we consider sodium, sodium has a chemical driving force into the cell. So this is the CDF. It also has an electrical driving force into the cell, which is the EDF. Okay. And if we think about potassium, potassium has an inward EDF, but an outward CDF. So the chemical force moves it outward according to its concentration. But the electrical force, because it's positively charged, moves it in the opposite direction, which is into the cell. Okay. All right. And now if we think about the total ECDF, so combining the forces, that would be the fourth step here, is considering both of these forces and summing them to arrive at the electrochemical driving force. So with that in mind, now we can think about sodium having a strong force because both of its forces are in the same direction. We're going to combine those two values, and that's going to be a strong force into the cell. And that specific equilibrium potential would be 130 millivolts. For sodium. And remember, we said that the distance away from the resting membrane potential really indicates the strength with which sodium wants to move. So sodium wants to get to 130 millivolts. So there's a strong magnitude that is rushing sodium into the cell because it's really far away from its equilibrium value. Let's look at potassium. Potassium is going to have a weaker force simply because the forces are in different directions, opposite directions. And so potassium has a weak force out of the cell. And if we subtracted the -70 millivolts at rest from potassium's equilibrium potential, we would get a very weak value, so a very small number of 24 millivolts. But potassium's equilibrium potential is -94 millivolts. This is where potassium is at home. So it's very close to the resting membrane potential, which is why we have a weaker force. Although we have more permeability, although we have greater permeability, the strength, right, the force, the magnitude with which the potassium wants to move is going to be weaker or smaller. Okay. Actually, I'm going to re-say this here. Let me correct this. This should be -24. So this is basically the distance between potassium's equilibrium potential and the resting membrane potential. So this should be -24. Okay, so this means that the equilibrium potential for potassium is -24 when compared to the resting membrane potential. For sodium, sodium's equilibrium potential is actually +160. So it's really 130 millivolts away from the resting membrane potential. All right. So just to put those numbers in perspective here. So we have the chemical driving force, which is a reflection of the equilibrium potential for potassium. We have the electrical driving force, which is really a reflection of the membrane potential, which is at this time -70 at rest. And then the difference between that is the force with which potassium wants to move. And if we make note of the same for sodium, the electrical driving force, again, reflection of the membrane potential. The chemical driving, oops, I did this wrong. Okay, yes. The chemical driving force is going to be +60 for sodium. And so because they're in the same direction, we're going to combine those two numbers, and this is the strength of our movement for sodium. Okay, so basically combining the electrical and chemical forces, and that will give you the strength or the ECDF with which the ion wants to move. All right, any questions? Any questions on reviewing this? So as I mentioned earlier, this is extremely important to understanding how we can excite the cell, basically thinking about what ions are at movement, what ions are moving when the cell is at rest, and then thinking about opening up additional channels. So when we consider the action potential, we're going to think about other channels on the membrane, not necessarily the leak channels that we're looking at here, but there are other channels that are concentrated along the axon of the neuron that are going to be important in moving sodium into the cell, which is what initiates the action potential, okay? So that is really the basis for understanding the action potential. Yep, so someone asked about the ECDF for potassium again. So the ECDF, we think about the two forces acting on potassium. If you look at the concentration gradient for potassium, potassium is at a greater number inside the cell. Again, thinking about our sodium-potassium pump here, greater concentration of potassium inside the cell and a lower concentration of potassium outside the cell. So the chemical driving force, which is the concentration gradient, is moving potassium out of the cell, okay? The electrical driving force is going to be based on the polarity, so the separation of charge, as well as the type and amount of charge on the ion in question. So because potassium is positively charged, and because we have a negative environment inside the cell, which was established because there's more sodium leaving, now we want potassium to move into the cell according to its electrical driving force. All right. So when we combine those two forces, because they're in opposite directions, we're going to consider the stronger force, which in this instance is going to be the chemical driving force, right? The chemical driving force, which is a reflection of where potassium is at home, which is the equilibrium potential for potassium. So this is a greater number than the electrical force acting, which is a reflection of the membrane potential at rest. And so the overall direction of movement of potassium is going to favor the stronger force, which is out of the cell. All right. Accordingly, we're going to subtract. So we're going to take the bigger force, subtract the smaller force, and that would be the strength with which potassium moves, which is -24, and the overall direction in the direction of the stronger force, okay, which is out of the cell.